In the previous video, we explored how temperature changes affects the dimensions or the properties of solids. And we used that to suggest that we can use solids to measure temperature by looking at the change in the properties of the solid and then casting that as a calibration to temperature. But we immediately abandoned that idea because solids don't behave regularly with temperature changes. So what they do is that they expand little, very little, too little. You will need a large amount of heat to deposit in it before it expands for you to appreciably see it. So they are not the best for us. We abandon them. But while we abandon the idea of using solids to measure temperature, we don't have to abandon these formulas because they are the same formulas that apply for other substances, liquids and gases. They also apply. They are universal for all substances. So in that case, we will keep them along and we won't try to derive them from scratch again for liquids and for gases. Just know that the properties of substances like volume, length, and area change with changing temperature. So today we want to talk about calibration, how to calibrate a liquid and glass thermometer. We already established previously that the expansion of substances is in response to temperature. There is kind of a correlation between temperature change and the expansion of substances. We are going to lead with the following proposition. Liquids behave the same way in response to temperature change as solids, but it's just that they are better at what they do. What we are going to do is to try to find the lowest point that everybody on Earth will agree on and find the highest point that everybody on Earth will agree on. And then in between, we can then just get the scale by dividing the space in between into some units based on the range, the temperature range. Okay, here's what we are going to do. We will define what we feel is very cool, the very cool, that's one extreme, and what we feel is the very hot. Okay, so we can just say steam point is very hot, okay, and ice point is the very cool. So if you put this tube in ice and there is a temperature decrease, you mark that point as 0 degrees. We assume that the temperature of the solid doesn't change significantly. It doesn't expand in response to the temperature. So that way we can be rest assured that when it receives the heat, it transfers it directly to the liquid so that the liquid expands and we see the change. So with this assumption in place, I'll put this particular tube in ice, we'll get the ice point. And when we put it in steam, boiling steam, and when water is boiling and you put this in there or you put it in steam and make sure that the equilibrium is reached. Equilibrium meaning that you know that this thing is now stable and there is no change. But if it is still, it keeps rising, you don't stop until it stops and you know that this particular temperature is almost the same as the temperature of the water. Then you also mark that as the steam point. Now we have 2 points on the thermometer. Let me redraw it in here to illustrate that. Okay, we have 2 points. 1 point is 0 degrees Celsius and another point is 100 degrees Celsius. Okay. The distance between the 0 degrees Celsius mark, the distance, let's just say height, okay? The distance between the 0 degrees Celsius and the 100 degrees Celsius can then be divided into equal units, 100 equal units. So the range from here to here is 100. So we can divide the distance. Let's say H2 minus H1 is just H. So we'll take H and divide by 100. So we'll get how many meters or how many units or how many centimeters or millimeters will move before we make a mark to mean 1, okay? And the next mark to mean 2, to mean 3, to mean 4, to mean 5, to mean 6, and so on. So in this case, after we are done with this, we now have a fully functioning thermometer to measure our temperature. Notice how I did not specify the thermometric liquid. The liquid in the tube is always called thermometric liquid. So we just said a thermometric liquid. So it will be the same for mercury, alcohol, and maybe water. Okay. Now, once we are done with calibrating our thermometer, we can go ahead and use it. So when you then put this particular thermometer in somebody's fridge and the temperature goes down to, the height goes down to this point, okay? Then you then extrapolate. Let's say it goes down to 1 degree Celsius. Then you then say, okay, it goes down to, let's say 1 millimeter, okay? Because the length is measured in meters. So if it is at 1 millimeter in this at this point corresponds to what? Here. Okay. One last thing I would like to point out before I move on is that your thinking might be something like this. But liquid is kind of liquid. So if you're going to measure, you have to measure their volume, not height. But I think we can resolve that by understanding that the volume in this case will be equal to the cross-sectional area times H. Okay? So when the liquid is rising, all of this has the same cross-sectional area. Okay? So over here, the cross-sectional area is the same as here. So the only parameter that is changing is the distance between one cross-sectional area and another. So instead of saying that the temperature change is directly proportional to the volume, you as very savvy people will know that the change in temperature is also dependent on what is changing the volume, which is the height. So in this case, we let it depend on the height of the column instead of just the volume of the column. Take a look at the length formula for temperature expansion carefully. I'm going to write an analogous formula of it on the next page for the height of the column. The height of the column, let's say H2, will also be equal to the height at H1 plus the coefficient of expansion. The coefficient of expansion times the height at H1 times the change in temperature. So you can go back and confirm this on the length and area expansion formulas. Now, when we have this relationship, we know a few things are constant, okay? This height might change to a new height, but this is constant, okay? This particular height might reduce to like a new height, let's say H, okay? So once we know that that can change, let's just say the height changes. So once we have H1 minus H2, and we also have T1 minus T2 or T2 minus T1, and their ratio is a constant, which is this, H1. Okay, this is what we can infer from this. H1 over T2 minus T1 is equal to constant. Now that we know that this particular proposition is correct, let's explore the following relationship. When you have H2, from H2 to H, there is a change in height, okay? And the change in temperature that corresponds with that is this. And from H2 to H1, there is also a change in temperature. And this corresponds to 100 minus 0. Okay. So in this formula, if you know the heights, if you can measure the height H, and you also know the height at 0 degrees Celsius and the height at the boiling point, 100 degrees Celsius, you can easily calculate any temperature in between, any height you take, any height you measure. You can easily calculate any temperature without even the calibrations. So the point is, if they give you a thermometer that is not calibrated and they give you some arbitrary height of the thermometer, you can calculate the temperature at that height based on the freezing points and the boiling points, or the ice points and the steam points. Let's use these example values of the height to calculate the temperature Tisa at the height 5 millimeters. So our H2 is 10 millimeters and our H is 5 millimeters. That divided by 100 degrees Celsius minus theta is equal to, our H2 again is 10 and our H1 is 2, and over 100 minus 0. So in this case, you have 5 over 100 minus theta equal to 8 over 100 degrees Celsius. So this is a linear equation that you can just solve for the value of theta. And we solve for the value of theta as follows. If you do a cross multiplication, you end up with this. 800 times 100 minus theta is just 800 minus 8 theta is equal to 5 times 100 is 500. So you group like terms and you end up with 8 theta is equal to 300. And if you divide both sides by theta, you end up with theta is equal to 75 over 2. 75 over 2 is exactly 37.5 degrees Celsius. And that's how you calculate temperature from an uncalibrated thermometer. You can do this if you go to the hospital and they give you a thermometer to do something without calibrating it. Okay, we are now going to look at the behaviors of the different liquids. We'll start with water, the commonest liquid we know. Water has an unusual behavior around 0 degrees to 4 degrees Celsius. So this was what we were expecting. Let me take you to the graphs for alcohol and the graph for mercury, and we contrast that with water. This is mercury. Mercury starts growing linearly from some temperature, like after it has melted to liquid. It starts growing linearly, expanding linearly with respect to temperature or due to temperature changes. But here, let's see what water does. All this flat line, the flat line from all the way to the negatives, is water just saying that it can't respond to temperature because it is at that point not a liquid yet. So if you are going to measure temperature around this area, that's no more water. That's ice you're talking about. So we can't be talking about this region. This region is ice. Apart from the ice region, there is this region. This region is where it's now water, and our expectations are that the water should start expanding, should start doing something like this. But it doesn't. It doesn't do that. Instead, from 0 to 4 degrees Celsius, it starts shrinking. It starts contracting. When it contracts until 4 degrees Celsius, then it starts expanding until it gets to 100 degrees Celsius. So that is a weird behavior. Its range is already low. 100 degrees Celsius is the range. It's already a low range, and it is misbehaving between 0 and 4. So it is a bad thermometric test. It doesn't serve its purpose very well. So even you could argue that why don't we just take from here to here? But here to here is pretty small for us to calculate our temperature. What about if you want to measure 0 degrees Celsius or 0 degrees Celsius or 3 degrees Celsius? What are you going to do with that? So the point is not that water is very bad at this. It's just that water doesn't behave well. So since it doesn't behave well around this area, it's cutting its range. The range is important. how wide is the range at which you can accurately tell us temperatures. That's important. It's already small, 0 degrees Celsius to 100 degrees Celsius. And it's cutting off 4. So it's left with 96. That's pretty bad. So let's see what mercury has to offer. From negative 144 degrees Celsius all the way to 357 degrees Celsius, mercury works. It is at this point that mercury becomes a solid. So we don't consider it to be changing with temperature. We are considering liquid mercury. So all the way from negative 144 degrees Celsius to 357 degrees Celsius, mercury expands linearly with temperature and hence can be used as a good thermometric liquid. So mercury is a better thermometric. The other properties, they are quite interesting. You can look at them. The other properties are that water is very clear and you can't see it in a glass, while mercury, you can see it in a glass. There are quite other properties apart from the anomalous behavior of water. This is called the anomalous behavior of water. So the behavior is quite anomalous, and that's where the name came from. Anomalous expansion. It kind of contracts instead of expanding and then expands at 4 degrees Celsius. That is called anomalous expansion of water. Now, for alcohol is also good, just way better than water, and it is just a little bit worse than mercury, but it's good. The range is quite high, more than 100 degrees Celsius, which water had, but it's not up to mercury. And it also expands linearly at all points with temperature changes very well. So it's a good thermometric liquid. That is why alcohol and mercury are used as thermometric liquids, but water is not. We move to another contender for thermometers, and gases are the best at this. They are good at what they do, and they do better than all the others we have mentioned so far. So why are gases good? Gases are good because they behave linearly with changing temperature over a long range. Unlike mercury that has a range from negative 114 degrees Celsius to 357 degrees Celsius, gas thermometers have much larger ranges. So they even extend to the temperatures like the lowest negative temperature. Apart from that, they can extend as far as possible unless they get ionized and don't behave linearly with temperature anymore. But they go as far as they can. So when you take any gas at all and you want to plot it on the V versus T graph, this is how it's going to look like. Say the volume of the gas was taken to be at some level around here, and you draw the linear graph. It's going to extend up this way. And the thing is that even though all the other substances stopped, liquids stopped at some points, this one continues. And it's linear. It doesn't have the anomalous expansion of water, and it doesn't stop at a very small range like alcohol and mercury. It just continues. Unless the gas turns to plasma state or it changes state to a different state, then the whole linearity thing stops. Okay, but there is something interesting. When we extend to the negative temperatures and we extrapolate it to see what the intercept on the t-axis will be, we find out that the value at the intercept on the t-axis is negative 273.15 degrees Celsius. This temperature is called the absolute zero. The absolute zero temperature is the temperature at which this particular volume is zero. Obviously, you can see that on the t-axis, there's no height up, so there's no further. So imagine it like the gas shrinking to the extent that it doesn't have any dimensions anymore. You can't see the volume. You can't see the volume of the gas. So the gas technically vanishing or something. And at this level, the gas cannot move at all. But talking about the gas this way is very strange, okay? Because physically they can't do something close to this like this. These are models and they work within ranges. Let me tell you what gas we'll be using. We won't be using real gases like oxygen, hydrogen, and so on. We'll be using a concept, an idealized version of gases called the ideal gas. And the ideal gas is just an idealized concept. It's a gas that you kind of imagine stripping away all other constraints. I mean, you put constraints on it so that the mathematics will work. The mathematics will be simpler. And once you get the ideal concept very well, you can go ahead and add a lot of, you can relax all the other constraints to get the math to be complicated if you want to work with the complicated mathematics. But right now, we'll be working with an ideal gas. I'll tell you in a moment what ideal gases are. Okay, back to the graph. When you take another volume of gas, you find out that it doesn't matter what quantity you take or what the conditions are. And when you extrapolate it, it doesn't have a different intercept on the t-axis. All of them cut the t-axis at the same point called the absolute zero. And this is pretty interesting because it shows us that gases are very consistent, and they show us that we can't continue freezing forever. We can't continue decreasing the temperature forever. There's a temperature range where it's impossible for the math or the physics to work. All of these, we are taking different volumes. We are kind of changing the volumes and seeing what happens. While we are doing all of that, we are keeping the pressure constant. What we are doing is we are seeing how volume changes with temperature as we keep pressure constant. So P1 represents when you keep P constant and you vary the volume with the temperature. This is this linear graph you obtain. P2 represents when you keep another arbitrary constant pressure and you change the temperature and see what happens to the volume. Okay. The other thing is the opposite can happen. You can try to keep the volume constant and check what happens to pressure when you change temperature. It turns out the same thing happens. The same thing will happen for pressure. Pressure will decrease to zero and it will happen still at negative 273 degrees Celsius. And this shows that all activity stops at absolute zero. The pressure being zero would mean that the gas no more has any energy, no kinetic energy anymore. They have literally stopped moving. And there is no motion, there's no activity at that point. Their properties have already gone. Like the maths just literally breaks at that point. It is impossible to kind of obtain that temperature and see what happens. So there is no way you can physically reduce the temperature to that, even if you tried so much. And then there is this scale called the Kelvin scale. The Kelvin scale is actually not any different from just the normal degree Celsius scale. The only difference between the Kelvin scale and the degree Celsius scale is that they are off by 273.15. And why was that change necessary? It was necessary because we wanted to shift the 0 to negative 273 so that we can have all our temperatures being positive and starting from 0 and onward, and there will be no negative temperatures. Instead of keeping track of what negative is, we just want the lowest point to be at 0 and all other points follow from there. So imagine we shift this axis, V axis, to the left. We shift it all the way to the left until we get to negative 273. To shift it 1 degree to the left would mean we add 1 degree to every point on the horizontal axis. So if we add 1 to 0, 0 becomes 1, and then negative 1 becomes 0. So you see, we have shifted it to negative 1. If we add 5, 0 becomes 5, and negative 5 becomes a 0. And with that in mind, we want to shift it to this point, negative 273.15 degrees Celsius. We can shift that way by adding positive 273.15 degrees Celsius to it to make this whole place 0. So our 0 has now been shifted here. And what always happens to the 0 point? The 0 point will always tend to the number you are adding, which is 273.15. So we have a new skill. But, well, why don't we still keep our old skill and also keep our new skill since people need time to adapt? So we'll change this to a different unit. We'll call it Kelvin. And that is how the Kelvin temperature scale came about. And this still exists. 0 degrees Celsius is 273.15 degrees Celsius. So knowing the transformation geometrically like this, the formula now comes naturally. T, temperature in Kelvin, will be equal to theta, temperature in degrees Celsius, plus 273.15. You can drop the 0.15 because people sometimes approximate it to 273. So 273 degrees Celsius added to your temperature in degrees Celsius will give you a temperature in Kelvin scale. Now, after we got that point pinned down, I now want us to come and talk about ideal gas. The gas we'll be using throughout. In the whole of thermodynamics, you'll be using an ideal gas, the ideal gas concept. Until you want to make the mathematics messy, then you go for the relaxations of the assumptions, and you can deal with the math. Assumptions we make for an ideal gas, the particles that make it up should be point masses. And in physics, when we say point masses, we mean literally like a dot without any dimensions, a dot that doesn't occupy space, but still has mass and still can move. That's what we want. Okay. That's actually not possible. If once you don't occupy any space and you don't, the very definition of matter is that matter is anything that has mass and volume. So once you assume that the thing doesn't have volume, or the thing has negligible volume, and neglect the volume. If you neglect the volume, you neglect the particle like that. So that's why an ideal gas is not actually real. Okay, so particles should be point masses. Another way this one is stated is that the volume of the particles should be negligible as compared to the volume of their container. So the other thing is about an ideal gas is that the molecules shouldn't attract each other. There shouldn't be any attractive forces between the molecules or force of repulsion. So that means, first of all, we haven't neglected their masses, but we just think that the gravitational force between them is negligible, and it really is negligible. And also, we don't think they are charged, because if they are charged, we'll get into trouble with electrostatic force. So there should be no intermolecular forces between them that will reduce their energy. Okay, the next thing is that we want the gases to move in random. Okay, the next thing is that we want the gas to move randomly. They should move in random directions. When they hit the wall of the container or they hit one another, they should move in random directions. And when we say random motion, we don't mean they should be curving and moving in curves and all of that. They should still move in straight lines, but the motion should be random, not that they move in one particular axis, or so they don't move in only x-axis or y-axis, or so they move in random directions, but still in straight lines. Perfectly elastic collisions. It means when the molecules collide, they should still retain their energy, their momentum should be conserved, and the energy should also be conserved. So this sets the stage for us. The mathematics will now be a lot simpler. We won't have to account for lost energy when there is no perfect collision, and we'll know that they move in straight lines in random motions. We can handle that. For the randomness, we can handle that. And there should be no intermolecular forces, which will in turn cause a loss of energy. And also, the particles should be point masses so that we won't have to deal with the particles themselves, or the particles that make up the particles themselves, or the molecules. We won't have to deal with the components of the molecules themselves before we come to what it contributes to the system as a whole. So the mathematics is a lot simpler now. We can now go ahead to use ideal gas, but basically we will be talking about the macroscopic level of it. We won't be talking about this, but this is just brought so that you know what an ideal gas is and why the assumptions are true, so that you don't go questioning some of the mathematics we'll be deriving or later on. There are laws that govern the way the gases behave, and various scientists took the initiative to test them experimentally and establish those laws. The first of those laws is Boyle's law. And Boyle's law investigates the relationship between volume and pressure when the temperature is kept constant. So you can go look up how the experiment is done, but think of it like keeping the temperature constant and increasing the volume to find out what happens to the pressure. Does the pressure increase or decrease? So what you will find out is that the pressure decreases when the volume increases. PV equal to constant can kind of be rewritten as T is inversely proportional to V, or the other way around. So in that case, you can introduce a constant, P equal to K over V, and then you get back to the same thing. Yeah, the constant you introduced, V is equal to that constant. Okay, and what will this particular constant depend on? Yes, remember we kept the temperature constant, okay? So first, PV is equal to T, but it should still be multiplied by something, because this is dimensionally inaccurate. Volume times pressure giving you temperature, this is dimensionally inaccurate. And in physics, when your dimensions don't match, then it's wrong. But first of all, I have to state something in addition. I have to formally state the Boyle's law. The Boyle's law states that given a fixed amount of a gas, or given a fixed mass of a gas, know that mass and amount of substance are kind of interchangeable, because mass is proportional to the amount of substance present. Okay, so given a fixed amount of a gas at constant temperature, the volume is inversely proportional to the pressure. This is a restatement of Boyle's law with another fixed quantity, which is the amount of the substance. Okay, and now experimentally, they found out that there is another constant of proportionality. Let me not say another constant of proportionality, because that's just the constant of proportionality. The other ones are just things we kept constant. So we kept 1, 2 constants, and then we were trying to see what happens. And after that, the postulate was that PV will be equal to NT. But then we need a constant of proportionality, and even adding the amount of substance to T doesn't still make this thing dimensionally accurate. So these two intuitions should inform you that there is supposed to be a constant of proportionality. So in this case, this constant of proportionality is R. This is the ideal gas equation. So we have just derived the ideal gas equation from the Boyle's law. Okay, there are other gas laws we need to look at. The next law is Charles's law. And Charles's law investigates the relationship between temperature and volume when the pressure is constant. So this is how it is stated. Given a fixed mass or amount of a gas at constant pressure, the volume is directly proportional to the temperature. V is directly proportional to T at constant N and P. I'm adding the N there for a reason. The amount of the gas present affects the volume. So if you introduce more gas into the system, the volume changes and you won't get a true relationship between the volume and the temperature that you want. So we keep both constants and we vary temperature and see what happens to volume. Let's play the same game as before with this one, synthesizing the ideal gas equation from the law, in this case Charles's law. So V is directly proportional to temperature, and we already know that the relationship between V and T is this, okay? And the other constant is N. And finally, the general constant of proportionality, we call it the universal gas constant. Universal gas constant. Okay, so this is the ideal gas equation. PV equals to NIC. Again, we derived it from another perspective. Once we already know the relationships exist, we can take a lot of shortcuts to get to the points, because like Charles, after finding out that V is directly proportional to T, won't immediately know that V is inversely proportional to P if Robert Boyle's didn't do the experiment prior to him. So in this case, we can take mathematical shortcuts without being scientifically penalized for it, because we already know the relationships. So we are not just doing algebraic gymnastics. The other thing you have to know is that when a process is occurring at a constant pressure like this, we call it an isobaric process. Isobaric process. So if it is at constant temperature, as we explored here, it was constant N and T. As we explored here, the process will be called isothermal process. Isothermal process. Isothermal and isobaric. And the next law is Gay-Lussac's law. Gay-Lussac's law states that at constant volume, he also held volume constant to investigate the pressure and temperature relationship. And he found that given a fixed mass of a gas at constant volume, the pressure is directly proportional to the temperature. Again, I mean, it's kind of boring to be playing the same game of synthesizing the ideal gas equation from these laws, but let's do it again, okay? P is directly proportional to T, and we know that P is also inversely proportional to V, but another thing was held constant, and that was the fixed mass, okay? So with this relationship, we introduce the proportionality constant RTN over V. This is not natural, so we write it the natural way, nRT. Okay, so in that case, we have again synthesized the ideal gas equation from the Gay-Lussac's law. And the last thing to be said about this is that a process occurring at constant volume is called an volumetric process, or an isometric process, or an isochoric process. I don't know why it has a lot of names, but it's interesting to know it does. Well, Once you have the ideal gas equation, PV equals nRT, a natural extension of your thought is that, why don't I keep another thing constant and see what happens? Okay, so what if we keep the pressure and the temperature constant? And we already know that R is constant. What will happen? So we see that V is directly proportional to N. And this is called Avogadro's law. So Avogadro's law simply states that at constant pressure and temperature, the volume is directly proportional to the amount of gas available. This is general constant temperature and pressure, but not at standard temperature and pressure. Constant temperature and pressure, constant temperature and pressure means that it could be any value. Both of them could be any values they want. It could take any values. And then stay constant at those values. But standard temperature and pressure, often shortened as STP, standard temperature and pressure, means that it should be standard. Standard atmospheric pressure or standard pressure is 1 atm. And standard temperature is 273.15 Kelvin. And as we demonstrated before, 273.15 Kelvin on the Kelvin scale is equivalent to 0 degrees Celsius on the Celsius scale. And also, if the unit of pressure, atmosphere, is unfamiliar to you, we will change it to a unit that is much more familiar, pascals. 1 atm or 1 atmosphere is equal to 101,325 pascals. Okay, and it's sometimes approximated to 100,000 kilopascals. And you know, the 1,000 in the 100,000 kind of represents kilo as a prefix, and that becomes 100 kilopascals. So 1 atmosphere is about 100 kilopascals, approximately. So these are specific values of the temperature and pressure, which are constant during this examination of the volumes change against the amount of substance present. And they are called standard temperature and pressure. They are universally agreed on. There is nothing special about them. We can wake up today and say that room temperature is the standard temperature, and that will be accepted if we all agree. So, given that these values are now known, we now have some knowns, and we have the only unknown being volume, because we can take 1 mole of a gas or any number of moles of a gas. But here in this case, let's take 1 mole of a gas and we solve for what volume responds to that with a given temperature and pressure. So we use that with the value of the universal gas constant, and we find that the volume of a gas at standard temperature and pressure is 22.4 decimeter cube. And that is called the molar volume. So now that we know all the 3 gas laws, we can combine them together into what we call the combined gas law. So the first one is volume is inversely proportional to pressure. And the second one is volume is directly proportional to temperature. And again, the last one is volume is directly proportional to the amount of gas present. If we combine all of these 3 dependencies, we'll have volume depending on NT over P. And if we introduce a constant of proportionality into this equation, we will have V equal to the constant of proportionality times the amount times temperature divided by pressure. So a simple rearrangement makes this to be PV over NT is a constant. Knowing that this is a constant, at some initial pressure P1 and initial volume V1 and an initial amount N1 with an initial temperature T1. This particular configuration will be the same when you move to a different set of conditions like P2, V2, N2, and T2. And this is the general form of the combined gas law. It is useful in calculations, but we know that we could have used the gas laws independently to solve equation if we want to. When you set the number of moles in the initial stage to be equal to the number of moles in the final stage, then you have the moles being constant. So in that case, looking at the fractions on both sides of the equation, the n can cancel out, leaving you with a simpler version of the combined gas law. There was one last thing I needed to talk about before I move away from the concept of temperature. Without it, the concept of temperature wouldn't be complete. It's called the Zeroth Law of Thermodynamics. It says that if two systems are in thermal equilibrium with a third system, then the two systems are in thermal equilibrium with each other. What this means is that when you have a system A and it has the same temperature as a system B, and you also have another system C which has the same temperature with the system B, then A and C are in thermal equilibrium. This is kind of mathematically true too, because you have if you have A equal to B, then you have C equal to B, then it means A is equal to C.